So let's start. So this is the first lecture of the series of linear regression. So in this lecture, we are learn about the geometric intuitions behind our linear regressions. Okay. So in previous chapter, we have learned that logistic regressions is a simply classification technique. We call this is a regression, but actually it is a classification technique. Okay, but this linear regression, it is originally a regression technique. It is actually a regression technique. Okay, simply for regressions I am just using REG. Okay, so in classifications technique we have two classes. Simply its actual output, that is called yi. It belongs to some natural number n, that is 1 2 3. We have to separate these classes, but here actual output, it belongs to real number. Okay, now just before going to the mathematics, just see the geometric intuitions. So this is when we learn the generalized linear model. When we learn the generalized linear model, then we learn depth of its mathematics. Okay, but it is one kind of linear model, one kind of generalized linear model. Okay, in linear, that is linear regressions is called one kind of generalized linear model. It is. So let's start. So let D is our data sets, which belongs to data sets xi and yi, and I is belongs to 1 to n. Suppose D means data sets. It may be train data. In general, it is maybe train data. It is a train data set. And xi, it's a n-dimensional point. Means what? We have n number of features they have, and n number of data points they have. So simple, without any confusions, let's take our features vector of our data sets is D. Simple D, we have D features mean our xi is belongs to RD, and here yi belongs to R, because we are going to regression. But when we learn, because actually you have seen that in logistic regressions, yi actual output of the data is not a real number. It is a set of natural number, that is -1 +1 or 0 1 or elsewhere. For multi-class classification or elsewhere, but here it is a real number. Actual output is a real number. Okay, so for this we call here it is a real regression technique. But in such cases, yi belongs to +1 or -1. Sorry, simple, it is a +1 or -1, or it is simply 1 2 3. That is simple subset of natural number. Okay, now let's go to its geometric intuition. Of the logistic regressions. So to going to the geometric intuitions, let's consider it. Let's play with an example. Okay, let's play with an example. So our example here is that we have to predict the height. Okay, our example is, main objective of this example is we have to predict the height. and we are all know that height is all a real number. Simple. Height, a human height is always belongs to a real number. It is not a natural number. Means what? Its height it we call 157.6 semi, or anyone called 160 semi, or anyone called 161.75 semi. Simple. We see that it is like a real number. So to predict a height, to predict a human height, we have some features. So what we have the features? So our features is our given features is what? That is we called weight, we call gender, or authenticity. It's also a important features to predict the height of a human. Ethnicity, and as well hair color. So here we have taken these 5 features. First one is our weight, second one is our gender, third one is our ethnicity, fourth one is hair color. Here we have taken these 4 features. Okay, or other language we call it F1, F2, F3 and F4. So let's draw a picture first. Okay, suppose here this independent side, this is one you already know about. This is called the independent axis and this is called the dependent axis. Means in dependent axis we have one features, that is F1. Simple, it is our weight of any human, and in the y axis here we call y. Simple, y means what? That is dependent axis. We for what? It is our we have to predict the height, that is height. Okay, this is the so simple here for simple here we are taken one criteria, one features here. So easy of our visualizations, we have taken only one features. Okay, so let's take our data set is like that. Let's take this kind of data set we have. So in simple knowledge, you all know if height increases, if weight increases, in general, typically in general, if weight increases, then the height of human being are increases. It is typical concept, not always. There may be always exception, but in typical, if our weight is increases, then height is increases. So let's this kind of always exceptional here. There have 2 points that are exceptional for it. Here may be point, maybe they have point. Okay, but here you can see that. Here the best fitting of this data, the best fit of this data is our blue line. We have to fit that line, the line that touches maximum number of points. So here you can simply see that here blue line is the best fit of the data. Simply it is one thing called X. Okay, so in linear regressions, first objective is that we have to find this kind of plane, this kind of line or plane. In 2D we call line and 3D we call plane, and in ND we call it as a hyperplane. Okay, so main objective of our linear regression simple, we are calling here linear in LR. In short, we are calling In linear regression, main objective is that our find a line or plane or hyperplane that fits the given data. Just that's fit our given data. Okay. So simply here we have to at the end of the day we have to find this equation of the line. In this example, in this 2D system, we have to find the equations of this line. So in general, what we know, the equations of the plane. We know that equations, any equations of the plane in 2D is y is equals to mx plus c. Okay, in 12th standard we have already learned about these concepts. What is all about c? It is the intercept term and it is the slope term. Okay, c is called our intercept term and is here. W is called our m is called our slope. So simply in these situations, what will be the equations here? So if we convert these equations to this system, here what we call here y is mean what? Y is mean our height. A means what? We call is A means W1 of X mean weight plus C as we call it at W0. So simple. Here Y is this, W1 this and this. This is our main linear regression. Okay, this is our main linear equation. Now just see this thing. Here we are just taking this concept in 2D. Okay, just see this thing in 3D. How would it be like? Okay, I think this maybe it will be better. Okay. Okay, just see this thing in this. Just omit this. Okay. So let in these directions we have features 1. That is what is our features 1? That is our weight. Simple for weight we are using WT. In this direction let's our features 2. Let's here our features 4 F4. That is our hair color. And in these directions we have our dependent vector, that is y. That is we have to predict the height. Okay. So here we have two features. We have two features in this 3D, in the space of 3D. If we have two features, so our independent variable, that is we call that xi, have two component, that is xi1 and xi2. Okay, and xi1 is for what? xi1 for our weight, responsible for our weight, and xi2 is responsible for our hair color. Okay, now just if we put the point in this plane, now we are just putting this point. Suppose let's take our point will be here, that is xi. if we put this plane this here, so our suppose let's this is our xi1, and let's this is our xi2. So if we put, then corresponding we have also this point corresponding we have also yi, that is belongs to real number. Let's take yi is lie on this plane. Suppose let's draw the plane. Suppose this is our plane. And the yi is lie on this plane. Suppose this is our yi. Okay, so in this 3D, what will be the now our equations? What will be our equations? So first we have to write our dependent variable, that is our height that we want to predict. Sample the slope corresponding to our features 1, that is called w1, into what? Into our f1, that is our weight. Similarly for w2 into features 2, that is f2, plus interceptor term, that is called w0. Okay, and this is the main equations. If we put our data, that is xi yi, then how the equations will be? Yeah, that is our output, original output is what? Yi wi. If this point fit in our this actually this point is fit to our plane, then the equations will be w star into xi1 w2 into xi2 plus omega naught. If we just see this term, just see this term, this is mean what? This is mean w transpose xi. This is mean what? Simply because if we just see w transpose xi means w is also, if just here we have taken the two features, so our weight vectors also have two features, and our xi. So just you can see it. Now the main objective is, here is our given data, this kind of data we have given. Now our final objective is we have to predict line in 2D, plane in 3D, and hyperplane is ND in ND. So the main objective, just write down our main objective now. What? So now main objective is find a line or plane or hyperplane that best fits to the given data. At the end of the day, we have to find it. Just now to visualize thing, now let's take again our 2D example. I think in 2D it will be very easy to visualize it. Now let's take sample the 2D example. Okay, so let's I am not here using x or sample f1 f2. Here just in a independent axis we are using x, and for dependent variable we are using y to calculate it. Okay, and let's our given data is all about this type of data we have given. Let's here its own data and here its own. Okay, now you can easily see that to best fit of this data is what. So just see the green line. Green line is the best fit of this data. Okay, so now the main question is that what about this data? Now we have to play using these two data. So if you just remember it, in logistic regressions our fx is what? In logistic regressions our fx is simply the distance of the point to the plane, means w transpose xi, that we call f of x, simply f of xi, f of xi. Now here our f of x is the linear equation. So here y is equals to our f of x, that is simply our here linear equation. Means what? Means here w1x plus w0, because here we are considering the 2D example. So here our f of x will be these equations. If we consider the 3D equations, then we have to insert one component extra. So that is totally depend on our dimensions. What will be our, so here if we consider 2D, so our equations will be line. If we consider 3D, our equations will be plane. If we consider ND, then our equations will be hyperplane. So don't worry about it. So this is our equations. So this is our given data. So let's take this is our x1 data, this is our x2 data, and suppose these are well fitted. So let's any one of these. Suppose let's take this one. This is a well fitted to our plane. So let's take this is our x3 data. So what will be the output of x1 data? So our x1 data output will be, so first x1 data output will be y1. What y1 means? What y1 means f of x1. F of x1 means what? F of x1 means w1 x1 plus w naught. Okay, but you can see this, sorry, here will be our output data, this one, but here our given data is what? Our given data, let's take it is given data is x1 y1, here given data is x2 y2, here given data is x3 y3. Now if you just see this, here x1 is here and y1 is here. Similarly x2 is here and y2 is here. Just see this data. If we see this data, then it is our x3 and simply it is our y3. Now just see the first data, first x, that is x1 y1 data. So our actual given output is y1, but from the equations of our plane, what will be don't be confused about it. These equations we are using for logistic regressions, but these equations here we are calling for linear regression. Okay, now just see here our equations, our plane, our actually predicted, this is called the predicted output. This is called the predicted output, and y1 is called the actual output. actual given output. Okay, so what will be the error? Means our actual output or minus output, predicted output. So here that is for this point x1, so you are just call it the error 1. So error 1 will be what? Our actual output, that is called y1, minus our given output, that is called y1 hat. Okay, because this is not lie on the line, so this will be different. And so easily you can see here, this point actually y1 tilde, y1 hat, and this is our y1. So this difference is called the error 1. Similarly here, this point difference is this point, so it is y2, and our predicted output will be y2 hat here. So this difference is called the error 2. Here it is called error 1, and here y3 predicted hat as equals to our y3. Okay, for this point. So our error 1 will be this, and now what will be our error 2? Similarly we are just writing it SSLY in symbolically. So our error 2 will be what? So y2 minus y2 hat, and error 3 will be similarly y3 minus y3 hat. Okay, now just you see that we have to fit the best fit given data. And simple best fit means what? We have to clear this concept. Best fit mean what? Best fit means we have to minimize the error. Error means what? Error means this error 1, error 2, error 3. We have to minimize the sum of the error. Okay, so just the concept best fit. Best fit means what? So best fit mean we have to minimize the sum of the error. Okay, sum of the error means sum of the error is error. I is dependent on our number of data sets. Okay, hence if we languagely if we write it, that is minimum of sum of errors, minimum of sum of errors across our training data. Okay, this is the main thing. Okay, now I think you are all about clear what is error and what is the best fit. Okay, I think all the geometrical intuitions you have clear. Okay, just revisit this concept. So here simply in regressions we have to fit the baseline plane or hyperplane in the given data. That will minimize the error. This is the main objective of these geometrical intuitions, and I think you are all clear about that of this lecture. And now next lecture we are seeing how to find its mathematical equations to minimize this error term. Okay, now I think this is all about clear. If you have any problem about the geometrical intuition, just comment below.